Here we're going to calculate an interesting sum involving the even values of the Riemann-Zeta function. So we want to look at the sum as n goes from 1 to infinity of zeta evaluated at 2n divided by n plus 1 times 2n plus 1. And just to recall, if you evaluate zeta at 2, you get the sum of the reciprocal of the squares, which is pi squared over 6. And if you evaluate zeta at 4, you get the sum of the reciprocals of the fourth powers. In other words, 1 over 1 to the fourth plus 1 over 2 to the fourth plus 1 over 3 to the fourth, and so on and so forth, which is equal to pi to the fourth over 90. And in fact, all of these even powers have nice formulas involving rational numbers times powers of pi. And to evaluate this sum, we're going to use 3 tools. And the first one involves an integral formulation of the Riemann-Zeta function. And we'll just prove it in this special case where we're plugging in a positive even integer. But this is actually okay for lots of values of the zeta function. Okay, so let's get to this first. So I want to start with this right-hand side. So we have 1 over 2n minus 1 factorial, and then the integral from 0 to infinity of x to the 2n minus 1 over e to the x minus 1 dx. And now let's notice I can take this integrand and multiply the numerator and the denominator by e to the minus x. And that's going to put it into a more useful form. So notice now I have 1 over 2n minus 1 factorial, and then the integral from 0 to infinity of e to the minus x times x to the 2n minus 1 over 1 minus e to the minus x dx. But now that denominator looks like the sum of a geometric series, and so that's exactly what we'll use. So we'll use the fact that 1 over 1 minus u is equal to the sum as m goes from 0 to infinity of u to the m. And that's true if u is in the open interval containing minus 1 and 1. But notice, for x values between 0 and infinity, e to the minus x is in that right spot, except potentially at 0, but we could clear that up by changing this to a limit as x approaches 0, but we're not going to worry about that right now. And now we're going to rewrite the integrand while exchanging the order of summation and integration, which we're allowed to do because of the dominated convergence theorem. So that allows us to write this as 1 over 2n minus 1 factorial. And now we have this sum as m goes from 0 to infinity of the integral from 0 to infinity of e to the minus x, x to the 2n minus 1. And then we're taking that 1 over 1 minus e to the minus x and rewriting it as e to the minus x to the m, which is going to be e to the minus m times x. And now we have dx. Okay, great. So now I want to put that together a little bit. So notice this is going to be 1 over 2n minus 1 factorial. And now we're going to have this sum as m goes from 0 to infinity of the integral from 0 to infinity of x to the 2n minus 1 times e to the minus m plus 1 x dx. Okay, good. Okay, so now I'm going to bring this 1 over 2n minus 1 factorial inside of everything. Write that down, and then we'll bring that to the top. So now we have this is equal to the sum as m goes from 0 to infinity of the integral from 0 to infinity of x to the 2n minus 1 over 2n minus 1 factorial. And now we have e to the minus quantity m plus 1x dx. Okay, great. So like I said, I'll go ahead and bring that up and we'll move to the next step. So let's see where we are. We took the right-hand side of this identity, which we're trying to prove, and we rewrote it as this infinite sum of an improper integral. So we have the sum as m goes from 0 to infinity of the integral from 0 to infinity x to the 2n minus 1 over 2n minus 1 factorial e to the minus quantity m plus 1 x dx. So here we have a polynomial function times an exponential function. So that points towards using integration by parts. So our u part of our integration by parts will be the polynomial because it becomes simpler when we take the derivative. And then our dv portion will be the exponential function. So like I said, I'm going to let u equal x to the 2n minus 1 over 2n minus 1 factorial. I'll include that constant in the denominator as part of the polynomial. But now notice that taking the derivative here, we see that du is equal to x to the 2n minus 2 over 2n minus 2 factorial. Because bringing this 2n minus 1 down, it'll cancel the portion of the factorial down to just 2n minus 2. Okay, great. And now our dv portion will be the exponential part. So dv will be equal to e to the minus quantity m plus 1x dx. Now taking the antiderivative here, we see that v is equal to minus 1 over m plus 1 e to the minus m plus 1 times x. Good. And so those are all of the pieces that we need in order to use the integration by parts formula, which, just to recall, that is the integral of u dv equals u times v minus the integral of v du. Okay, so now let's go ahead and put all of that into our integration by parts formula, and that's still inside of this sum over m. So here we have this sum. M goes from 0 to infinity. And now we'll have u times v. Those are outside of the integral. So notice that's going to be minus 1 over m plus 1 times 2n minus 1 factorial. And then we'll have x to the 2n minus 1 times this exponential. So x to the 2n minus 1 e to the minus m plus 1 times x. And then we need to evaluate that from 0 to infinity, keeping in mind that evaluating at infinity means we're taking a limit. Okay, good. Now we need to do minus the integral of v du. Notice that v includes a minus sign in it, so the minus signs will cancel, and we'll just have plus 1 over m plus 1 times this exponential times this guy right here. So let's see what we get for that. So that's going to be plus 1 over m plus 1. And then we have 2n minus 2 factorial. And then the integral from 0 to infinity of x to the 2n minus 2 times this exponential. So x to the 2n minus 2 times e to the minus m plus 1x dx. Okay, good. But now notice if we quote unquote plug infinity into this, using L'Hopital's rule a couple of times, we'll see that we get 0 there because the exponential decay function will kind of dominate the polynomial function. Furthermore, if we plug 0 into this, the polynomial function goes to 0, but the exponential function is 1. So that means all of this right here becomes 0, and we're just left with this second portion. But notice all of that is still in the sum over m. So this is equal to the sum as m goes from 0 to infinity of 1 over m plus 1. And now we have the integral from 0 to infinity of x to the 2n minus 2 over 2n minus 2 factorial times e to the minus m plus 1x dx. So check it out. We ended up with something pretty similar to what we started with. We're just multiplying by 1 over m plus 1. So now let's see what we've got going on here. We've got the sum m goes from 0 to infinity, this integral 0 to infinity x to the 2n minus 1, and then all of this other stuff. And that worked down to almost exactly the same thing, except with the addition of this m plus 1 in the denominator. And instead of having a 2n minus 1, we have a 2n minus 2. And that points to doing repeated integration by parts until this x to the 2n minus 2 term becomes a constant. And so how many times would we have to do integration by parts until that was a constant? Well, we would have to do exactly integration by parts 2n times until we get that thing down to a constant. And each of them would have the effect of giving us an extra m plus 1 in the denominator and changing this from 2n minus 2 to like 2n minus 3 factorial, 2n minus 4 factorial, all the way down until we're 0 factorial, which is 1. So just to like continue, so I'll just put dot, dot, dot. This is equal to this sum as m goes from 0 to infinity of 1 over m plus 1 to the 2n. Again, continuing this process, doing integration by parts over and over and over. But that is exactly the definition of the zeta function evaluated at 2n. So that means we've established this first formula. And now we're ready to work through our second tool, which is a limit. So notice we're taking the limit as x goes to infinity of 1 minus e to the minus x over x squared minus 1 over x. And we want to show that that's equal to 0. So I'm actually not going to write anything up here because this is actually pretty straightforward. Notice as x goes to infinity, 1 over x is going to go to 0. And then e to the minus x is going to go to 0 as well. So this entire term goes to 0. This numerator goes to 1, while this denominator goes to infinity, which means this entire term also goes to 0. So in other words, we've established this limit. And now we're ready to move on to its more interesting companion limit, which is the same function, but now we're taking x to 0. So let's go ahead and look at that. So we have this limit as x approaches 0 of 1 minus e to the minus x over x squared minus 1 over x. Good. So now as x approaches 0 here, we have something that's like infinity minus infinity, which points us towards an indeterminate form, which can be rewritten in order to use L'Hopital's rule. So we'll combine these fractions, and I'll do that by writing this as x squared in the denominator and then an x in the numerator. Now combining these together, we'll have the limit as x goes to 0 of 1 minus x minus e to the minus x all over x squared. So I reordered things a bit when I combined them together. Now notice as x approaches 0, the numerator is approaching 0 because we have 1 minus 0 minus 1, and the denominator is also approaching 0. So that points towards an indeterminate form that can be evaluated with L'Hopital's rule. So let's go ahead and do that. So we can rewrite this using L'Hopital's rule by taking the derivative of the numerator and the denominator. So that's going to give us minus 1 plus e to the minus x all over 2x. But now, again, sending x towards 0, we see we have a 0 over 0 indeterminate form, so we can use L'Hopital's rule again. That'll give us the limit as x goes to 0 of minus e to the minus x over 2. But now we no longer have an indeterminate form, so we can just plug in x equals 0, and we'll see that we get minus 1/2, which is exactly what we wanted to show over here. And now we're ready to tackle our main result, which is this sum. So the first thing that I'm going to do is I'm going to write every zeta function here using its integral representation. So that's going to allow me to rewrite this as the sum as n goes from 1 to infinity of 1 over n plus 1 times 2n plus 1 times 2n minus 1 factorial. And then this is all multiplied by the integral from 0 to infinity of x to the 2n minus 1 over e to the x minus 1 dx. Okay, good. Now I want to do a couple of things. First of all, I want to notice that I almost have a perfect falling power here. I'm just missing a couple of terms. Notice if this looked like 2n plus 2, that would be a little nicer because it would be more in line with these terms. So I'm going to go ahead and exchange this n plus 1 with a 2n plus 2, and I can do that by multiplying the numerator by 2, because in fact what I've done is multiplied the denominator by 2. And then also I seem to have a gap here. I go straight from 2n plus 1 to 2n minus 1 factorial. So I'm going to go ahead and insert a 2n here as well by multiplying the numerator by 2n. Okay, good. So now I'm going to rewrite this, exchanging the order of integration and summation, and then factoring some things out kind of as needed. So I'm going to write this as the integral from 0 to infinity of 2 over e to the x minus 1. So I'll bring the e to the x minus 1 and this 2 out of the summation. And then I have this sum as n goes from 1 to infinity of 2n over 2n plus 2 factorial times x to the 2n minus 1 dx. And let's just notice that all of that is inside this integral. Good. Now what we want to notice is that this object right here looks like it is something that has had its derivative taken. Because notice we've got a multiplier of 2n, and then our exponent here is 2n minus 1. So what I'm going to do is write that as the derivative of something, and we can do that in the following way. This is the same thing as the integral from 0 to infinity. I still have 2 over e to the x minus 1. And now this is going to be the derivative with respect to x of the sum n equals 1 to infinity of x to the 2n over 2n plus 2 factorial dx. Good. So let's just talk our way through that real quick. So now if I term by term differentiate this, let's see what happens. So notice this 2n is going to come out front, and then my exponent is going to decrease by 1, so I have 2n minus 1. Okay, fantastic. Now the next thing that I want to do is make this exponent match with this factorial that I have down here, because this is starting to look like a somewhat common sum. And so I'll do that by taking this 2n and adding 2 to it. But in order to do that, I need to put a 1 over x squared out here. And notice that 1 over x squared is inside the derivative. Okay, so let's just go ahead and write that down. So now we have the integral from 0 to infinity of 2 over e to the x minus 1. And now we have the derivative with respect to x of the quantity 1 over x squared. And now we have this sum as n goes from 1 to infinity of x to the 2n plus 2 over 2n plus 2 factorial. And then dx. Okay, great. So now I'd like to re-index this sum so that this looks like x to the 2n, and then we have just a 2n factorial down there. And so I can do that by sending here n is going to n minus 1, and that's going to change my starting point to n equals 2 to infinity instead of n equals 1 to infinity. So that's going to give us, we still have this integral from 0 to infinity outside of everything, 2 over e to the x minus 1, and then this derivative. So we've got the derivative with respect to x, and then we have a 1 over x squared. That's still there. And now we have this sum as n goes from 2 to infinity of x to the 2n over 2n factorial dx. Okay, good. Now I'll go ahead and bring that up and we'll move on to the next step. So let's see where we are. We took our goal sum, and through a bunch of transformations, we got it down to the following integral. So it's the integral from 0 to infinity 2 over e to the x minus 1. Now we have the derivative of 1 over x squared times the sum n goes from 2 to infinity of x to the 2n over 2n factorial. Now what I want to do is rewrite this sum so that it starts at n equals 0 instead of n equals 2. So I can do that by adding in the n equals 1 and n equals 0 terms if I subtract them as well. So I'll add them in by changing that 2 to a 0, and then I'll subtract them by subtracting 1 and x squared over 2. So let's go ahead and talk about why those are the ones that we have to add in. Notice if we set n equal to 0, then we have x to the 0 over 0 factorial, but that's just 1. And then if we set n equal to 1, we have x squared over 2 factorial, but that's just 2. So I have indeed added in the 0th and the first term here and subtracted them off here. Okay, so now we're good to go. Now I want to do a callback to one of my previous videos where we calculate section sums. And notice that if we take this 2 right here and think about it as being connected to this series right here, we get exactly e to the x plus e to the minus x. So notice the even powered terms will double up, which is why we get the 2, but the odd powered terms will cancel. So I urge you guys to check out that video or just like check these details on your own. So maybe I'll just go ahead and summarize that by this little fact. I've got this square blue box, which are those two guys over there, and that's equal to e to the x plus e to the minus x. So we'll just use that. Okay, great. So now that means that I can take this integral and I can rewrite it in the following way. So I've got the integral from 0 to infinity. I have 1 over e to the x minus 1. And now I have the derivative of the quantity 1 over x squared. And then I'm multiplying by e to the x plus e to the minus x. So that's that blue part right here. Okay, good. But then notice also I have this -1 and this minus x squared over 2, but those are also being multiplied by 2. So that's going to give me a -2 here and a minus x squared here. And then I have dx all on the outside. Okay, great. So now let's go ahead and simplify this as much as we can. So we've got the integral from 0 to infinity, 1 over e to the x minus 1. And now I have, this is the derivative with respect to x of, so let's see what we have. We have e to the x over x squared plus e to the minus x over x squared minus 2 over x squared minus 1. And that derivative is with respect to x. Okay, great. And now let's just go ahead and start taking these derivatives and see what we get. So here we have the integral from 0 to infinity on the outside, 1 over e to the x minus 1. And now this derivative is going to become the following. So we'll use the product rule on this term first. So that's going to give me e to the x over x squared, and then minus 2e to the x over x cubed. Great, here we're thinking about this as e to the x times 1 over x. Now we get something pretty similar here, except both of them are attached to minus signs. So we get minus e to the minus x over x squared, and then minus 2e to the minus x over x cubed. Okay? And then notice the derivative of this with respect to x is going to give us a plus 4 over x cubed. And then finally, the derivative of a constant with respect to x is 0. So we'll just finish it off with a dx. Okay, so now this is the integral that we want to calculate. I'll go ahead and bring that up and then we'll get to it. So we got our goal sum down to the following integral. So the next thing that I want to do is do some careful transformations on this integral. But before I do that, I want to kind of combine like terms. So I'm going to rewrite this as the integral from 0 to infinity. I have 1 over e to the x minus 1. Now I'm going to go ahead and put this guy together with this guy. So that's going to give me e to the x minus e to the minus x. That's all going to be over x squared. Okay, good. And I'm going to put all of the rest of the terms together, and those are all over x cubed. So notice I'm going to have plus 4 minus 2e to the x minus 2e to the minus x, and that's all over x cubed dx. Okay, great. Now the next thing that I want to do is factor a 2 out of this. So I can do that. That can be written as 2, and now we have 2 minus e to the x minus e to the minus x. The next thing that I want to do is motivate a factorization of this. And I can do that in the following way. I'll take this 2 and rewrite it as 1 plus 1. And I'll take one of those 1s and I'll write it as e to the x times e to the minus x. So this whole thing becomes 2 times e to the x times e to the minus x plus 1 minus e to the x minus e to the minus x. Great. And then you can see that that thing in yellow will factor like e to the x minus 1 times e to the minus x minus 1. And so that allows us to take this entire thing and rewrite it as the integral from 0 to infinity of 1 over e to the x minus 1. And now we have this term, which remains the same for now, e to the x minus e to the minus x over x squared. And now we have this 2, so that's going to be plus 2. And like I said, this yellow part is going to factor. So this is e to the x minus 1 times e to the minus x minus 1. And that's all over x cubed. And then dx. Okay, good. And now I'm going to do something similar to this term. So I'll factor an e to the minus x out of this. That allows me to write this as e to the minus x times the quantity e to the 2x minus 1. Great. But again, that thing can be factored as well. So notice this is equal to e to the minus x times e to the x minus 1 times e to the x plus 1. Great. So now let's see what cancels. So notice in this first term, this e to the x minus 1 cancels with this e to the x minus 1. And in the second term, this e to the x minus 1 cancels with this e to the x minus 1. And so that leaves us with the integral from 0 to infinity of, So all we're left in this first term is with e to the minus x times e to the x plus 1 all over x squared. Good. And then what we're left in the second term is plus 2 times e to the minus x minus 1 all over x cubed dx. Great. So we're simplifying our integral one bit at a time. I'll go ahead and bring that up and then we'll finish it off. So we got our goal sum down to this integral. Now we want to continue to simplify. So I first want to notice that I can multiply this e to the minus x through, and that's going to give me a 1 plus e to the minus x, because I have e to the minus x times e to the x. So like I said, that's going to be 1 plus e to the minus x. Great. And then I can multiply this 2 through similarly, and that'll give me 2e to the minus x minus 2. Okay, so now let's spread those apart and then recombine like terms. So here we've got, this is the integral from 0 to infinity of 1 over x squared plus e to the minus x over x squared. So that's what I get from spreading that into pieces. And then I have plus 2e to the minus x over x cubed, and then finally minus 2 over x cubed dx. So now I'm going to put these together a little bit. So this is going to give me the integral from 0 to infinity of 1 over x squared minus 2 over x cubed. So those are the terms without the exponentials. And then I have plus e to the minus x times the quantity, 1 over x squared plus 2 over x cubed. And all of this is within my dx integral. And now comes the trick, and the trick is actually taking the antiderivative of this. So notice the antiderivative of this is pretty straightforward because we just have the power rule. So notice that's going to give us 1 over x squared minus 1 over x. So the antiderivative of that, we increase the exponent by 1 from -3 to -2, divide by the new exponent. Then the same kind of thing over here. Good. And then it's a little bit tricky to see the antiderivative of this, but if you notice, it looks like the product rule has been employed, and that's exactly what's happened. And what you can see is that the antiderivative of this is exactly equal to negative e to the minus x over x squared. Okay, good. So let's just go ahead and talk our way through that. So notice if we take the derivative of this, so the derivative of e to the minus x is minus e to the minus x, so that's why that becomes a plus. And then the derivative of 1 over x squared is 2 over x cubed, so that gives us that other term. Great. And then we need to evaluate this from 0 to infinity. So now what I want to do is put those together a little bit, and I'll put them together so they look like this. So notice this is exactly equal to 1 minus e to the minus x over x squared. In other words, I'm combining like denominators, and then minus 1 over x, and then like I said, evaluating at 0 and infinity. Keeping in mind, evaluating at infinity requires a limit, and evaluating at 0 also requires a limit. And notice, evaluating at infinity will give us 0, and evaluating at 0 will give us minus half. But since that's the lower bound of integration, we have the opposite of that. In other words, we have 1/2. So we've got the goal series has a sum of 1/2. And that's a good place to stop.